consensus for renewability are wind turbines and solar panels. So that's what my career was focused on. And as we all know, the pace of deployments for wind and solar has steadily increased over decades, starting back in the 1980s in some of the early wind project conglomerations in California, the three principal ones being Altamont Pass, the Tehachapi's, and San Gorgonio Pass near Palm Springs. Over time, renewables expanded to include utility scale solar, also of course rooftop solar, and it has further evolved to include battery electric storage. Over time, you can see the pace, hopefully folks can see my cursor, but the renewables market has accelerated in its deployments such that now today, the deployments from 2021, as you can see, the vast majority of new megawatts that were built in the United States came from wind and solar, with a relatively small portion being provided by things like natural gas. There's a little bit of battery electric storage. Really, no one is developing things like coal-fired power plants anymore. I couldn't tell you a single credible proposal anywhere remaining in the United States. That was not the case 20 years ago, but it is the case today. So that's wonderful. But even with all of those investments, still renewable electricity only accounts for today about 13%, 14% of the nation's electricity usage. So significant scale of the effort, but we have a long way to go. So I've included a quote here from American Clean Power, which is the conglomeration organization from what was previously the American Wind Energy Association, and then its sister organization in solar. But really, if we keep on the path that we're on, we're really we are not on track to meet our own climate goals. We will need to accelerate the pace to achieve our renewable electricity goals. That's just focusing on electricity. That's before we take into account things like the significant energy demand in the fuel sector. So globally, only around a quarter of the total carbon problem is ultimately from electricity. To address the remaining 3/4, for most of the rest of the 3/4, we need something else. We need a fuel. So we believe, Eneus Energy believes that green ammonia is that fuel. and the reasons are simple. So for many uses, they're just not they're not amenable to being electrified. And so if you were to try to electrify them, you would suffer significant losses. There'd be infrastructure mismatches where you don't have the infrastructure where you want it, et cetera, et cetera. So one of the interesting things about green ammonia is that we are huge consumers of renewable electricity. To give you an idea of scale, a typical project development for us is on the order of 1,000 megawatts of load, so 1 gigawatt of load, which would be fed by around 1.5, potentially 2 gigawatts of renewable generation, wind and solar. So on the left, I'm showing a map of operating US clean power projects. So principally wind and solar, you can see where they are with respect to their online date and technology across the US. Interestingly, where they've been placed does not correlate well either to the wind resource in the United States or to the solar resource in the United States, at least not in great scale. So for example, you see concentrations of lots and lots of solar along the mid-Atlantic east coast. But if you look at the solar resource map, that's not where the best resource is. Similarly, you see lots and lots of wind projects up in the upper Great Plains. You see some wind resource up here, but you see a big purple swath through the middle of the country, which is where we find the premium wind and of course the premium solar is in the desert Southwest in the US. And that's not generally where you're seeing a lot of investments in utility scale wind and solar projects. And the reason for that is simple. The grid is simply full. So here we're showing an overlay of just the highest voltage transmission lines in the US with a simplified version of the wind resource map. And I'm assuming that generally the class is familiar with the fact that we have different electricity market structures in the US, East, West, and then the majority of Texas. If you drive up from the southern part of the United States, just kind of weave your way through from the Mexican border to the Canadian border, you can see there's very, very little transmission that is built out here in some of the windiest, resource-rich parts of the country. So what that means is that even though you're in the middle of the country, you're sort of at the edge of the system in terms of the electricity markets. And that means it's a challenging place in which to build large-scale wind and solar. It can be done, has been done, but there's a reason why people build more wind turbines and solar panels closer to population centers. Wouldn't it be nice if there was a way to bring electric load to the renewable resource, essentially build a great big electricity load, a consumer of the electrons in the places where we have abundance of wind and solar. And of course, that is feasible with technologies like wind and solar, or excuse me, with green ammonia and green hydrogen. So now let's spend a minute talking about the difference. Here we go. The difference between the two. So green hydrogen, for those of you who are familiar, is simply water that has been electrolyzed and divided into its components of hydrogen and oxygen. And we do that by feeding it with large volumes of renewable electricity. So two ingredients needed to make green hydrogen: just water and renewable electricity. Now, green hydrogen is the appropriate fuel for powering and decarbonizing all of the sectors you see down here. So some of the biggest ones that get the most attention today are oil refining, steel refining, power generation, even cement making, and injection into various chemical processes. Great. Vehicles also get a fair amount of attention, largely because they're more consumer facing, but this is actually one of the smallest sectors for us, powering fuel cell vehicles, whether it's passenger cars and trucks or commercial scale trucks and buses. And the reason why, so that's the target, market sector for many of us in green hydrogen. However, hydrogen in its hydrogen form is very difficult to store or transport. And in most end uses, it makes sense to do at least one of those two things, if not both. So therefore, it makes sense to convert the hydrogen into something else, in our case, ammonia, so that it is more easily stored and transported. To give you an idea of scale, if you were to take green hydrogen, or just hydrogen, regardless of how it was derived, and attempt to liquefy it for storage or transportation purposes, first of all, you would use around 40% of the embodied energy to get it into its liquefied state. So you have to overproduce by almost double in order to get the same end product that you would like to build. And then a hydrogen liquefaction plant is an extremely capital-intensive plant. That it's a very large investment. So it's difficult to justify in most cases. But then in order to move it, you have to keep it at conditions that are just about 20 degrees above absolute zero. So it's liquefied at negative 253 degrees, which is, again, 20 degrees above absolute zero. And boil off is very high. And so it's just, for many reasons, it's an imperfect solution for even hydrogen users. So what we do is instead, because we can't solve the problem with physics, is we solve it with chemistry. So we take the green hydrogen that we have now made in the first part of our plant and blend it with nitrogen that we derive from the air, which is about 79% of what we're all breathing right now. And those two together, hydrogen and nitrogen, form anhydrous ammonia. And anhydrous ammonia is a commonly produced chemical today. It's predominantly used in the fertilizer sector. Around 80% or so of green ammonia that's produced today is literally spread onto the dirt and crop fields to grow principally corn, but it is also used for soybeans and wheat and other crops. But it's a nitrogen carrier. It's also used in various chemical processes. It's used to make explosives. I have a bottle of it under my kitchen sink, and I use some of it to clean my kitchen floor. But it can be used, if it's made in a green way, it can be used to decarbonize many fuel uses. So, this becomes a much more efficient way to transport and store green hydrogen is by doing it in its ammonia form. We store it at much closer to ambient conditions. whether it's in a cryogenic facility or a slightly pressurized facility. Either way, much, much closer to ambient, and therefore less electricity, less energy goes in the process. To give you a comparator between green ammonia and how it is made and its equivalent product, its equivalent physical product of just conventionally produced ammonia. Today, the way it's made is for conventional ammonia, they start with natural gas through a process of either steam methane reforming or autothermal reforming. They extract the hydrogen from the molecules, from the natural gas molecules, utilize that and blend it with nitrogen to form anhydrous ammonia. But then in many plants, they release the rest of the natural gas molecules into the air. So it's an extremely emissions intensive process. So if you try to take conventional ammonia today and use it to, say, power a ship, for example, which is one of the key early adopters, we believe, for the green ammonia space, you wouldn't accomplish much from an emissions perspective because the process of making conventional ammonia is so emissions intensive. But we remove the first part of the plant, the steam methane reforming or the autothermal reforming. Natural gas does not come into our plant at all. And instead, our only three ingredients are renewable electricity, air, and water. And from that, we make a liquid fuel. I've got more slides, I will keep going, but I'm gonna pause here and see if there are questions thus far.
Yeah, I have some questions, Krista. So the nitrogen, you said that where do you guys get it from? You said from the air, is that right?
It is, yes. And so we use either an air separation unit, which takes the air and divides it into all of its component parts. So nitrogen, oxygen, some argon, et cetera. And it sends the nitrogen then into an ammonia synthesis loop using Haber-Bosch technology, which is from like the 1930s, and blends it with the hydrogen. So that's one way. Another is a little bit lower tech, and it's just simply called a nitrogen generating unit. But again, it derives the nitrogen from the air. It doesn't sort the rest of the air into its other component parts, which is why it's a little bit cheaper.
I see. Yeah. And my second question is, so you're saying that ammonia as ammonia can be used directly as a fuel, is that right?
It can be, yes. It's
but I mean,
one
what
of its.
I understand is like hydrogen is used to to run fuel cells, and you can get electricity out of it, right? But what kind of process can you use to have ammonia as an input fuel and get electricity out? What would be an example of that?
To get electricity out. So there are. So Mitsubishi is actively developing an ammonia-fired turbine. It's a 40 megawatt platform. They've been public about this. And then Wärtsilä and MAN Energy Solutions are both developing ammonia-fired reciprocating engines that also would be used to produce electricity. Both of them also can be used in a peaking capacity for anyone who's studying electricity markets. So you can make them run at a base load, steady output all the time, or you can make them fluctuate up and down in response to the demands of the transmission system, follow renewables, et cetera. So you can make them do a lot of things. Now that's if you're going to convert the molecules back into electricity. For the majority of uses, though, it's used to propel something. So this would be used to power a ship or to power an airplane or power a locomotive. As a carrier for the hydrogen would be steel refining, cement making, glass making, a lot of the heavy industrial sectors that don't get a lot of public attention, but are today extremely emissions intensive, and this is a way to clean them up.
There are a couple of questions in the chat. Maybe Maxi, do you want to read them perhaps?
Yeah, so one of the first questions is, what is the cost difference between producing green ammonia and traditionally produced ammonia?
That's a great question. So today, well, I'm going to turn the clock back about 2 years. So up until about 2 years ago, the cost of conventional ammonia was around $200 to $500 per metric ton. And it fluctuated a little bit based principally on natural gas prices and corn prices, if you can believe it. But it stayed generally within that band. In the last couple of years, we've seen it spike up to more than $1,600 per metric ton. That was in response to a few things. Part of it is supply chain interruptions that have impacted our economy generally. It was already, interestingly, it was already that high before the war in Ukraine started. And then the war in Ukraine has made it just that much worse and has further limited our supply chains. So today, actually, we can make green ammonia less expensively than than the market price for conventionally produced ammonia. Although, so that's one way to look at it. Another way to look at it is that in most cases, the thing we're replacing with green ammonia is actually not an ammonia product. It's an oil or a natural gas-based product. So there is a comparison to do with whatever we're replacing, but it's probably not ammonia. It is fair to say, though, that today, in a lot of end uses, there would be a green premium associated with green ammonia, but especially after you take into account things like current and anticipated carbon taxation, et cetera, on top of regulatory pressure, shareholder pressure, consumer pressure, et cetera, to decarbonize. This ends up being actually a pretty good economic bet.
Okay, and then the second question, it says, is it expensive to make and sell?
And so, well, kind of related to this question, all things are relative. There certainly is some cost associated with it. Interestingly, because our principal feedstock is the renewable electricity, our price of the produced and delivered ammonia is heavily dependent on the cost of the electricity coming in. Which is why it makes sense for us to site our plants in places where we have some of the fastest winds, the brightest sun, the highest quality renewable resource, because in most cases that translates into lower cost renewable electricity, which therefore means lower cost green ammonia.
Chris, I also have another question. So why is it then the hydrogen kind of like took the lead in, as opposed to ammonia?
That's a good question. So ultimately, what a lot of the end users are looking for, like the form they will use it in, is hydrogen, but that's fine. But the fact that they say we're seeking green hydrogen, or we're seeking green or blue hydrogen. Blue is just conventionally produced hydrogen where an attempt has been made to capture at least a portion of the carbon. So if a customer says they want green hydrogen or blue hydrogen, that's probably where they start, because that's the form in which they would use it. And then they quickly realize, oh, but I need to move it. Or even if I'm able to make it on site, I want to use it at some time later than when it was produced. So I must either move it or store it or both. And then they quickly realize that an alternative form of it, like green ammonia, is ultimately the preferred method. And then once it is stored, transported to the customer, stored on site, and then ready to use, then it is cracked back into hydrogen at the point or at the time in which it would be actually used. But you're right, that hydrogen is the one that has grabbed a lot of the headlines and has gotten a lot of the public attention, even when it will be done in the form of ammonia. We've actually noticed internally that in many articles that talk about a hydrogen economy or a hydrogen initiative by a government or a regulatory body, for example, the headline will say hydrogen. All throughout the article, it will say hydrogen, and down near the bottom there will be a paragraph that says people will likely do it in the form of ammonia.
Okay, so another question from the chat. Is green ammonia considered as green energy or renewable energy?
It's both. So it has the two pillars. It is zero carbon and it is renewable. And it's zero carbon both when it is produced and when it is burned. So in contrast, so if I took a ton of conventional ammonia and I tried to power, say, a ship with it, it would be zero carbon when it's burned, when it's utilized, but not when it's produced. Therefore, we cannot call it green. For us, for green ammonia, it's zero carbon and renewable throughout. And actually, I'll elaborate on that point just a moment. Because ammonia is the decarbonization fuel for many of the ways that we move ammonia, like in shipping, like in barge, like in rail, which we'll get to in here in just a second. we're actually able to show, so if I'm going to make green ammonia in Colorado or Kansas, or a place somewhere in the US maybe, and I'm going to send it to a customer in, I don't know, Germany, I can show that significant parts of the supply chain between, say, Colorado and Germany also were powered by green ammonia and therefore are zero carbon or lower carbon than they otherwise would have been. So actually, that's probably a good point for me to get back into the slides, because we do talk about transportation a little bit. So one of the reasons
there's
why—
another quick question here, maybe you can
Yes,
address
please.
that and continue.
Go for it. Another question.
Maxi, go ahead.
So it says, can green ammonia replace gasoline?
Ah, interesting. Yes, we believe it can. We believe that it needs to be blended with something else, and then it can be used blended with gasoline in conventional today's cars and trucks. So one of the big maybe not stumbling blocks, but challenges to overcome with things like fuel cell vehicles is that it requires new infrastructure to be built out. It at least requires hydrogen charging stations or hydrogen filling stations to be built out. Those are different than regular gas stations. It also, in many cases, requires either a truck logistics solution to be put in place to deliver the hydrogen to the fueling station, or it requires a new pipeline system to be built to deliver the hydrogen to these hydrogen fueling stations. And that's all well and good, but those are both very capital intensive. And in addition, pipelines are extremely, they have very long development cycles. So even if you were ready to write a check for a hydrogen pipeline today, there's development work to do. You have to go secure land rights from all of the landowners from point A to point B. You have to get permits. If you're going to cross a water body, you have to go talk to the U.S. Army Corps of Engineers, et cetera, et cetera. It can take many years to successfully develop a pipeline of any kind. And so one of the things that a company like us thinks about is, how do we use as much of what's in place today as possible without having to rely on build out of new infrastructure? And so this is actually something we don't spend a lot of time talking about publicly, but we do believe that there is a way to blend ammonia into gasoline such that, for example, my 13-year-old car could pull up to the regular gas station on the corner. I could fill my car with a blend of gasoline and ammonia, and I, as the consumer, wouldn't know the difference. I might only notice if the gas station owner decided to put a picture of a wind turbine on the gas pump, and that's it. So the fuel delivery system doesn't change, the fuel pump and the gas station don't change, and my car doesn't change.
Kristen, I have one more question before you continue. This
okay.
is interesting. So, say for example that I want to power a fuel cell with hydrogen, right? So the first thing that I need to do is to get the hydrogen, say, from water. For that, I'm going to need to input some energy, right?
Yes.
Call that energy 1 unit, okay? 1 per unit, if you will.
Okay.
Then, say if I want to go through the process to convert that into ammonia, I will first need to mix it with nitrogen, right? And
Yes.
there'll be energy input in there, right? And then eventually I'm going to have to just, you call it, crack it to separate the hydrogen from the nitrogen, right? And there'll be another energy input in there, right? So if you say you spend 1 unit of energy getting the hydrogen from the water, then the other 2 processes that require energy, that's just a small percentage of that initial 1 unit, or is significant or relatively?
It's a good point. It's a really good question, and you're absolutely right. Every time we convert the energy from one form to another or move it, there is a loss in some fashion. We had looked at this, our company had looked at this a couple of years ago and had quantified a scenario very similar to what you were describing. And we said, okay, from renewable electricity in to either liquefied hydrogen or to ammonia and then crack it back into hydrogen. So looking at those two to compare, the liquefied hydrogen had an energy penalty of about 40% to get it cold enough to convert it into liquid hydrogen. By contrast, the renewable electricity to gaseous hydrogen to ammonia cryogenic storage through a cracker and then back to hydrogen was only a loss of about 14%. So there is still a loss, but it was much smaller than liquefied hydrogen. And the reason why we don't talk about gaseous hydrogen is like a metaphor I use for people is it would be like sending a FedEx truck down the road with like 7 boxes in the back. Each box would be very, very expensive because gaseous hydrogen is so low in density. So in order to move it in any quantity as hydrogen, you would want to liquefy it. But for the reasons we just talked about, there are real challenges associated with that. And the same exact principle is true for storage too. So green ammonia is also, we believe, the right mechanism to use for long-term energy storage. So in recent years, we've definitely seen a huge uptick in battery electric storage systems, which is wonderful. Those pair very nicely with solar. They pair nicely with wind. If you want to move it 4 hours, 8 hours, something like that, battery electric storage systems are a good option. They can also be designed to operate to provide some of the ancillary services that transmission systems are accustomed to receiving from conventional power plants, things like frequency response, some voltage support, et cetera. So on the left, we've shown this photo is a couple of years old. As of a couple of years ago, this was the largest battery electric storage system in the world. It's in Australia. Other larger ones have been built since then, but same principle is true. It's still a very large battery system. So if we take that as a unit energy of 1, the amount of energy in terms of megawatt hours that it can consume, and then compare that to what is today, even still, the world's largest liquid hydrogen storage vessel, which not surprisingly is a NASA facility in Cape Canaveral, Florida. This has approximately 70 times the stored energy as the world's largest electric battery. And then compare that to a regular run-of-the-mill, fairly low-tech cryogenic anhydrous ammonia tank, and it stores more than 2,000 times as much energy as the world's largest battery electric storage system. So if you're an electric utility operator thinking about how to manage your system with things like gas-fired power plants and coal-fired power plants increasingly being decommissioned, and wind turbines and solar panels increasingly being built, and therefore there's a transition from conventional power plants to renewable power plants, it makes sense to think about not just the short term, day to day, hour to hour, how do I manage my system, but also season to season, how do I manage my system? In many places, the wind is best maybe during the winter or the spring, but we really need it in August, and there's very little wind in August, for example. If you want to store wind, you can do it in a tank for 6 months if you want to. It's effectively indefinite. And so for anyone thinking about time shifting at scale for significant periods of time, must look to green ammonia. Okay.
Okay, so one more question before we go on.
Please. Yes.
It asked, well, what, kind of going back to what we talked to before, will it affect the engine if we use this fuel, knowing that some manufacturers have a specific fuel specifications?
Good question. Are we talking about a car engine or what kind of engine?
I'm assuming a vehicle engine, I think, in regards
Okay.
to gasoline.
So the Environmental Protection Agency, EPA, maintains certain standards for what goes into fuel. So today, if anyone pulls up at the gas station and fills up their car, gasoline is the primary thing in there, but there are all kinds of additives and detergents and other chemicals that go into gasoline today, most of which are not readily known by the consumer. But the EPA manages essentially a window or threshold, like as long as you fall within within certain bounds of various additives, you're allowed to sell a fuel blend to consumers. Now, and the thing they use to determine whether a fuel fits within these tolerances is, will it damage the engine? Also, how is it for the environment? But would Ford Motor Company, would Chevrolet, would Toyota all look at that and say, yes, our engines will run correctly on that fuel without damage to it? And so the answer must be yes, in order to be allowed to sell fuel at a gas station to consumers today. And so the same would be true for ammonia. We must meet the EPA standards. Okay. All right, so we talked about this a little bit, but this is essentially how green ammonia is made. So we start with renewable electricity in, water in. The water can come from a number of different places. Ultimately, it all needs to be treated, and then it needs to be further demineralized. So it is just pure H2O coming into the electrolyzer. The output of the electrolyzer is the hydrogen, that is derived from the water. And then there is also then an oxygen vent. In most projects, we just kind of ignore it because we release it into the air because the plant is not located close enough to another oxygen user or consumer that it makes sense to bother capturing it. But if you happen to be located in the right place and you can capture it, then it can be a valuable byproduct. For most plants, we just ignore it. Then the hydrogen becomes the first primary input into the ammonia synthesis loop, which again utilizes Haber-Bosch technology, which originated in the 1930s. We blend the hydrogen with air, with nitrogen that's derived from the air using either an air separation unit or a nitrogen generation unit. And then again, there is an oxygen vent. So there's an oxygen byproduct, we can vent it and release it in the air, or we can capture it and sell it for medical equipment, industrial facilities, etc. There is also an occasional, depending on design, either an occasional sporadic or a continual, very small volume vent of ammonia fumes, just to provide a pressure release in the system. And then the output of this is the molecule NH3, which is anhydrous ammonia. For green ammonia and conventionally produced ammonia, if you put a tank of each side by side and presented a chemist with the two of them, they should not be able to tell the difference between the two. So how is ammonia moved today? There are 5 principal ways. Our company focuses on 4, and the reason is because the 5th is truck level, which is generally volumes that are too small for our company. So there's a mismatch. So the 4 primary ones we think about are pipeline, and really there's only one large ammonia pipeline system operating in the United States today, and we're showing it here in this map. It's operated by a company called NewStar. It originates down in southern Louisiana, near the port of New Orleans, and it fans up into the US Midwest, which is where a lot of corn is grown, and therefore there is a market for large volumes of anhydrous ammonia. There is a second large ammonia pipeline system that was in operation until about 2018, and it goes from West Texas up into southern Minnesota, but it has been decommissioned, so it is not operational today. And there are smaller, much shorter localized pipeline systems in various places along the US Gulf, but for big interstate transmission of ammonia, really the NewStar one is the only one that's operating today. And then in most places along its pipeline route, it is buried. So here, I took this photo, I was standing in Iowa. Here you can see the marker next to the side of the road where the pipeline crosses underneath. If there was no marker, you wouldn't even know it was there. So that's the ammonia pipeline method for moving ammonia. The next way to move it is by rail, and it goes in tank cars that look a lot like this. No surprise, there are train tracks crisscrossing throughout the United States. Some of them are enabled to be able to move ammonia. Not all of them are. There's a thing called positive train control that's required for safety reasons in order to be able to move ammonia on it. But this is how it is done in large quantities today. The third way to move it is by barge. So here, this is the inland waterway system. Essentially, it's our network of rivers throughout the eastern United States, where there is a significant amount of our economy that still moves by barge and tugboat, and ammonia is no exception. There's also a small stretch of the Columbia River in the Pacific Northwest that is ammonia enabled, and where ammonia can move by barge today. And then finally, it can be moved by ship. So we're showing an ammonia gas carrier here on the right, but shipping routes around the world are many. And here we're showing sort of it's almost a heat map of some of the busiest shipping routes. So this is, if we were going to make green ammonia in a place like Colorado and ship it to anywhere in the world, it is readily done. There's something like 120 ammonia-enabled ports globally, and I would expect in the next 5 to 10 years that number is likely to double.
So, Krista, are those existing routes for moving ammonia around?
So this map is just general shipping routes. So you're seeing cargo ships, you're seeing container ships, you're seeing ships of all kinds here.
Yeah, I mean, my question ultimately is the ammonia that is being moved around and sold and whatnot, as of today, is mostly used just as a fertilizer, correct?
That's correct. That's correct. Yeah. So from year to year, between 75 and 80% of the ammonia that's produced is sold ultimately as a fertilizer. And in some cases, it's applied to the soil directly in its anhydrous ammonia form. In other cases, it is blended with something else and converted into a different form, maybe a physical pellet that's spread on the field. But the end result is the same. It's a way of getting nitrogen into the soil. So it's a little bit of an irony, because for most of our customers, they're looking for the hydrogen, but for most ammonia customers today, they're looking for the nitrogen. Okay, so we've talked about all the ways that ammonia is moved today, and it is the from year to year, it's either the second, third, or fourth most commonly produced commodity globally. By contrast, there is a significant amount of hydrogen produced globally, but it's north of 99% is coming from steam methane reforming or autothermal reforming, and very, very, very little is transported. The little bit that is transported is transported by hydrogen, dedicated hydrogen pipeline networks. For example, the United States has a network of hydrogen pipelines along the Gulf Coast to feed heavy industry that's located from Texas over to Florida. But if you wanted to move it globally, today there's a total of one ship on the oceans that would move, would move hydrogen in its hydrogen form as cargo. It's a Kawasaki vessel. It was commissioned a couple of years ago. It moves liquefied hydrogen, and it only moves about 100 metric tons of hydrogen as cargo. And to give you a sense of scale, one of our facilities would be able to produce that amount of hydrogen in a few hours. So now, as we think about where this industry is going, we see broad consensus that between the two, green hydrogen and green ammonia, this is the key. These are the keys to global decarbonization, essentially all the things that we cannot reach in just electricity form by itself. So here I've shown a smattering of headlines, all sort of suggesting that this is where governments are going. Something like 70% of global GDP comes from countries with hydrogen plans or hydrogen targets of some kind. Increasingly, this is what heavy industry, this is what transportation, this is what our economy is looking to decarbonize. And we're very pleased to be a key player in that. So I've provided my contact information here. I'm happy to answer more questions while we're gathered here today. If there are questions following today, feel free to reach out. This is my contact information. Thank you very much.
That's it. Thank you, Krista. We appreciate your talk. It was very interesting. And let's now have the students ask some questions. So guys, go ahead. So there are a couple of questions on the chat. I will defer that to Maxi to read them.
Okay.
So one of the questions says, as far as the whole green hydrogen process is, the water supply negatively affects in the long term, and is the water still clean?
Is the water still clean after we produced the ammonia?
Mm-hmm.
Okay, so when the water goes into the electrolysis facility, the majority of it is utilized and split into its hydrogen and oxygen components, and then the hydrogen becomes the input to the ammonia synthesis loop, and the oxygen is either vented to atmosphere or potentially captured and sold as a byproduct. Some of the water, less than half, significantly less than half, is either recycled back through the water treatment facility and the demineralization facility, or it's treated as a waste stream and it's disposed of. That byproduct water or reject water is a more mineral dense water. So it's essentially a saltier water. And so depending on where the plant is located, we like I said, either reuse it or release it to some other to some other water treatment facility offsite.
Okay, so then related to the same, Krista, so say that the energy that is being utilized in these various stages, it all comes from, say, green power, why not? Or renewable, whatever you want to call it. So there is no waste coming out of this process, like no pollution at all? Like
So there,
to generate ammonia and then to use it, say, to run an engine or something or whatever it is?
there's a little bit of the waste, the stream in the water that we just mentioned. There's a little bit of ammonia gas that is released either occasionally, sporadically, for a pressure release, or in a very small amount continually to release pressure in the system. But otherwise, those are the principal byproducts or emissions, if you will. So very, very, very low.
Okay, so I mean, maybe I will ask, maybe if you can share with with the students, a lot of these guys are, students that are about to graduate, whether, from undergraduate or MS degree. So you've been very, I mean, I know you personally, you've been very successful, you have worked in various startup companies, related to technologies that involve risks, whatnot. So do you have any advice for the students in general, to become well positioned in various industries after they get out there?
Good question. We have a thing we say at Eneus, which is going green is a good bet. And I think that's true for professional development as well, for like at the personal level. Thinking of my own career, I started in wind development back when wind was cool. And I remember when I graduated from college with my bachelor's, I had a couple of job offers, and I chose to take the lowest paying one because it was in green energy. And I thought, there's something to this. There will be a future in it someday. And I am so glad I did. I'm sure the others would have been fun too, but I'm so glad I chose the path that I chose. And I will also say, if anyone has an interest in green ammonia development or really renewables development generally, this is a very good time to get in. We are seeing accelerated interest on the parts of many large companies to green their operations. And this is true throughout the economy. This is true of insurance companies. It's true of fertilizers. It's true of transportation companies. It's true of heavy industry. It's true of consumer products. You name it. People are sticking to their ESG targets, and we very much appreciate that. We expect it of them as consumers and as shareholders. What that means for us as professionals is that it's a good market to be in.
Perfect. Thank you so much, Krista, for sharing that. So there's a question from Professor Park here. Again, I will defer that to Maxi to read it, please.
So it says, I understand burning ammonia has the NOx or nitrogen oxide problems. How bad would this be compared to CO2?
Good question. So this is again a little bit of irony. So one of the uses for conventionally produced ammonia today is at coal-fired power plants in its scrubbers, in its selective catalytic reduction facilities, or SCRs. To get rid of things like NOx. So actually ammonia can be used to remove the NOx that would otherwise be released from burning it. So having it on site actually is quite helpful. Coming back to the ammonia fired engines and turbines that we talked about earlier in the presentation from Mitsubishi and Wärtsilä and MAN Energy Solutions. I think all three are public, that they sell an SCR standard with their equipment, and it would be ammonia would be the agent utilized in the SCR.
So are there companies here in the US developing?
There are more kind of all the time.
Power plants kind of thing?
Yeah, so today I think the chief use that people see for green ammonia in power generation is in a peaking capacity. So and that's a reflection of the fact that today the fuel is still expensive. in time, if the cost comes down, then it may make sense to operate it in more like a baseload fashion, but today it would be used as a peaker. But a very flexible peaker. Essentially, it would run just like a conventional power plant would, whether it's natural gas fired or coal fired, and it would be able to provide all of the same frequency response, voltage support, inertia that a conventional power plant would, but in a completely green fuel.
And are you familiar? Because I mean, I'm interested more kind of like in the power plant kind of aspects. Are you familiar, like, let's say, for example, scalability? Can you build power plants as large as you want, or there are issues?
So what we're seeing today is that for the ammonia-fired ones, the block sizes proposed are in like the 20 to 40 megawatt range. Now, it's also worth noting that all of the major gas turbine OEMs have issued, so like they're new. If you were to go buy a gas turbine today, it would be sort of hydrogen enabled out of the box, up to maybe 20, 30, 40%, depending on the manufacturer. And with fairly modest modifications to, I believe, the combustion chamber, you'd be able to co-fire a higher percentage of hydrogen with a natural gas blend. And there are some that they're saying, for example, Mitsubishi, I think, is saying around 2040 or so, they plan to have 100% hydrogen-enabled turbines. I think they will be, my personal projection is that they'll be able to meet that. And we're seeing plenty of customer demand for a product like that. And again, if you're going to burn it in its hydrogen form, you probably want to receive it and store it in its ammonia form.
Okay, pretty good.
Yep.
All right, so there is another question there, Maxi.
So what is the shelf life of the green hydrogen energy once again, and how long does the green hydrogen take to synthesize?
So the green hydrogen, when it goes into an ammonia synthesis loop, I mean, it's sort of synthesizing on a continual basis with a feedback loop and whatnot. So it's happening effectively in moments after you send it into the ammonia synthesis loop. If you're storing it in its ammonia form, you can store it in a fairly low tech cryogenic storage facility or storage tank for months if you want to, years maybe. And the way those work is they're chilled down to about -35 degrees Celsius. -33 degrees Celsius is its point at which it transfers from a liquid to a gas. So you keep it a couple of degrees colder than that, and it's just barely pressurized. So just barely. Now that's if you're going to do it in large volumes. If you want to do it in smaller volumes, then you typically would not do it in a cryogenic fashion, but rather in a slightly pressurized basis in maybe a bullet tank. And those are low enough pressure that you could achieve that with a bicycle pump if you wanted to.
Okay, very good. So any other questions from the audience at all? No, well, if not, then Krista, we will thank you once again. I thank you personally and on behalf of everyone here on the Zoom meeting. It's been very interesting. And yeah, students, if you guys have questions for Krista, or even you have interest in the industry, I mean, feel free to reach out to her, and who knows, perhaps she can give you a job. So anyways, yeah, so just a couple of things, guys. So we are going to have another seminar in 2 weeks from today at 11 as usual. I will send the invite as appropriate. And yeah, other than that, Krista, thank you so much. And I will send you an email with a follow-up email. We want your address or whatnot. I'll get in touch with you. But at this point, I just say publicly, thank you so much. I very much appreciate it. And I'm sure all the students, they also appreciate your talk. So thank you.
Well, thank you very much for the invitation. I appreciate it. It was a pleasure speaking with you all, and happy to answer any questions that occur to you after today. So thank you again.
All right, thank you so much. Bye-bye.
Bye-bye.